Boom. All right, ladies and gentlemen, welcome. This is the voice of Dr. Joliban. Okay, yeah, your online tutor. Introduction. I'm Dr. Joliban, here, PhD in Electrical Electronics Technology. I had my first degree in Uniben, second degree, that's master's in Uniben, then PhD from the Nnamdi Azikiwe University, OKA, aka Unizik. Okay, so but in this video, we're going to be discussing purely chapter 2 of your Chem 101. If you have missed the last video, for Chem 101, which is chapter 1, do well to go back to our playlist and check for chapter 1 and watch that video. It's very, very detailed, okay? Everything you need to know about Chem 101 chapter 1 is detailed arranged in that video, and even more materials that you will not see in your textbooks. All right? So, but in this video, we're going to be looking at the laws of chemical combination and quantum theory, okay? So, but what will happen is, because of how lengthy this chapter is, we are going to be looking at the laws of chemical combination and part of quantum theory. So in the second part of chapter 2, we're going to look at quantum theory and the configuration part in details. Okay, so boom, let's get started with the very first part, laws of chemical combination. And there are basically 4 laws of chemical combination, basically 4. The first is the law of conservation of mass. The second is the law of definite proportion, also called the law of constant proportion. The third is the law of multiple proportion. And then the fourth is the law of reciprocal proportion. Okay? So, and we take the first one, the law of conservation of mass. Now, the law of conservation of mass is championed by Landau and his co-workers, okay? So Landau and his co-workers actually championed this law. This law was actually propounded by them based on John Dalton's theory, which states that matter can neither be created nor be destroyed, but can be transformed or converted from one form to another. That is the basics of this law of conservation of mass. So according to Landau and his co-workers, the law of conservation of mass states that in a chemical reaction, mass can neither be created nor be destroyed. That is to say that the sum of the total mass of the reactant of a chemical reaction must be equal to the total sum of the product of that same reaction. No mass is lost in the process. That is what the law is saying. Now, the law is verified using Landau's experiment. The Landau's experiment comprises of a Landau tube that is H in structure. In that tube, one side of the tube you can have sodium chloride solution. The other side of the tube you have silver triazonitrate 5 solution. Of course, you take the weight before the reaction because the tube is privileged to separate the two chemicals from meeting with each other. So the weight is taken, probably it weighs 100 grams, and then the tube is now inverted and shaken vigorously and allow the reaction to take place between the two substances. And of course, when sodium chloride reacts with silver triazonitrate 5, a precipitate will be formed. A precipitate of what? Of silver chloride will be formed. A white precipitate for that matter. So that white precipitate formation shows a complete reaction, okay? So the white precipitate being formed will determine the completeness of the reaction, and then the weight will be taken for the second time. And if it gives you exactly 100 grams, that shows that the law actually is true. And of course, it is true from that experiment. So, but however, limitations in this law states that 1, it is only applicable in liquid substances or aqueous substances. You do not apply this law in solid or gases. Solid because solids react very slowly. You do not apply it in gases because the mass of gases are very much unpredictable, okay? So that is the very first limitation you can have as far as the law of conservation of mass is concerned. Then the second limitation is that the volume of the Landau tube expands, especially for reactions that are exothermic. You know, it expands and doesn't return back to its original shape. Then the last limitation you can have is that in the presence of sunlight, especially nuclear reactions, in the presence of sunlight, Landau's law doesn't hold. And the reason is because sunlight actually converts mass into energy. If you remember Albert Einstein's equation, mc squared, mass times light will give you energy. So it converts part of the mass into energy, which can be used, doped, and at the end of the day, the mass of the reactant becomes greater than the mass of the product. And so the law does not follow. So these are the limitations of the law of conservation of mass. Now that takes us to the second part, which is the law of definite proportion. Now, according to the law of definite proportion, also called the law of constant proportion, of course, first and foremost, it is championed by Prout in 1799. Prout in 1799 actually, discovered this law based on John Dalton's theory, which states that atoms of the same element are identical but completely different from atoms of other elements. Oh yes, atoms of the same element are identical, but they are completely different from atoms of other elements. So after a series of experiments performed by Prout, he stated that all pure samples of the same compound contains the same element chemically combined together in the same proportion by mass. All pure samples of the same element or of the same compound contains the same element chemically combined in the same proportion by mass. Take water for example. All pure samples of water contains the same elements chemically combined in the same proportion by mass. It comprises the same 2 atoms of hydrogen and 1 atom of oxygen chemically combined by mass. If the water is coming from the lake, if it is coming from the ocean, if it's coming from the well, it's coming from the sea, it's coming from rain, no matter where the water is coming from, when it is purified, it contains the same proportion by mass of hydrogen and oxygen. And that proportion is 1:8. 1:8, 1 from hydrogen, 8 from oxygen. Hydrogen is 1. The mass of hydrogen is 1. 1 times 2 is 2. The mass of oxygen is 16. So by the time you find the ratio, it gives you 1:8. That is the law of definite proportion, the law of constant proportion, right? So that takes us to the third law, which is the law of multiple proportion, championed by John Dalton himself. Yes, championed by John Dalton himself, based on his fourth theory, which states that chemical combination, or let me say atoms chemically combine together with each other in simple whole number ratios. That is the bedrock of this law of multiple proportion, championed by John Dalton himself. His statement that says that atoms chemically combine together with each other in simple whole number ratios prompted this particular law of multiple proportion. And this law states that elements, if 2 elements A and B combine chemically with each other to form more than 1 compound, then the several masses of A, which combines with a fixed mass of B, are in simple whole number ratio. Alright, let me give you an example on that. Let's say A be oxygen and B be copper, okay? Copper 1 to be precise. If oxygen and copper 1, that's a fixed mass of copper, combines chemically to form more than 1 compound, that is copper 1 oxide and copper 2 oxide, then the several masses of oxygen, which combine separately with a fixed mass of copper, are in simple whole number ratio. Do you get? So let's take a fixed mass of copper combining with oxygen. Now, the first copper combines with oxygen to give you copper 1 oxide. Then the second one combines with oxygen to give you copper 2 oxide. Now, the fixed masses of copper kept aside, those masses of oxygen which combine separately with copper are in simple whole number ratio. And the first oxygen there is half a mole, the second oxygen is 1 mole. By the time you do your ratio combination, you discover that it is in the ratio 2:1. And that is the law of multiple proportion by John Dalton. So that takes us to the third one there, which is the law of reciprocal proportion. And the law of reciprocal proportion actually is coined by Benjamin Richter Jeremias in 1792. Benjamin Richter Jeremias in 1792. And this law states that when elements A combines with 2 or more other elements, say B and C, then the several masses of B and C, which combines with a fixed mass of A, are in same or multiple of B and C, which combines with each other without A. I know this is a little bit confusing, but let me take it again. This law states that when an element A combines with 2 or more other elements, let's say B and C, then the several masses of B and C, which combines with a fixed mass of A, is the same or multiple ratio of B and C, combining together without A. To give you a typical example, a combination between carbon, hydrogen, and oxygen. Take, for example, carbon combines with hydrogen to give you methane. The same carbon will combine with oxygen to give you carbon dioxide. Now, hydrogen can actually combine directly with oxygen to give you water, right? Now, what the law is saying is that when an element A combines with two or more other elements B and C, that means when carbon combines with two or more other elements, hydrogen and oxygen, when carbon combines with hydrogen and oxygen, then the several masses of B and C, which combines with a fixed mass of A, then the several masses of hydrogen, and oxygen, which combines with a fixed mass of carbon, are the same or multiple ratio of hydrogen and carbon combining together without A. That simply means that the masses of hydrogen that combines with carbon, the masses of oxygen that combines with carbon, are in the same ratio or multiple ratio as at when hydrogen will combine with oxygen without including carbon. That is what the law is saying. And the best way to do that is always to put them in the ratio of their masses. Carbon combining with hydrogen will do that in the ratio of 12:4. 12 is to carbon, 4 is to hydrogen. While carbon combining with oxygen, we do that in the ratio 12:38. And when hydrogen combines with oxygen, we do that in the ratio of 4:16. So 12 grams of carbon combines with 4 grams of hydrogen. Then 1 gram of carbon, that's a fixed gram of carbon now, will combine with how many? And by the time you're able to do that mathematics, you store that mass of hydrogen. So you do the same for oxygen, store that mass of oxygen, and then find their ratio. You will discover that the ratio you are going to have for those fixed masses that combine with a fixed mass of carbon is going to be in the ratio of 1:8. Now check hydrogen combining with oxygen directly will do that in the ratio of 1:8 as well. So that is the law of Landau. I say Landau. That is the law of Benjamin Richard Jeremiah's. Other examples which you can use to work out this law of reciprocal proportion is oxygen combining with sulfur and hydrogen, and then phosphorus combining with hydrogen and chlorine, then the fixed mass of hydrogen combining with sodium and chlorine, So the ones at the top are always fixed masses, right? So you can make those experimental research and you get rid of that. So that takes us to the second part, which is I think this chapter is divided into 3. We go to the quantum number realm, but before we enter quantum number realm, we look at Niels Bohr's theory of the hydrogen atom. Very, very important. Niels Bohr's theory of the hydrogen atom. Now, according to Niels Bohr, when electricity is passed through a discharge tube containing hydrogen gas at low temperature, the molecules of hydrogen gas breaks down into hydrogen atoms, which eventually emits radiations. These radiations emitted are electrons. So once you pass electricity through a tube containing hydrogen gas, it breaks down the hydrogen gas and they emit their electrons. These electrons fall in the form of lines, and these lines can be viewed by the use of a spectroscopy or a spectroscope, as the case may be. Now, these lines are grouped under series and regions, okay? So you have series like the Lyman series, the Balmer series, the Paschen, the Brackett, the P-Fon. Sorry, there's nothing like P-Fon. It's the Fon series, okay? The Fon series, Humphrey, and further series. Then as for the region, you talk about the UV region, the visible region, the infrared region, and then the far infrared region, as the case may be. So now, let's look at the spectrum of line of the hydrogen atom. The very first ground state is a nucleus. After the nucleus, you have the first energy level, the second energy level, the third energy level, fourth, fifth, sixth, on the above 6th energy level. Now, the electrons that will be falling from the second energy level to the first energy level is the first spectral line of the hydrogen atom. The ones falling from the second to the first. Then the others will fall from the third to the first. Others will fall from the fourth to the first, the fifth to the first. All those falling on the first line are referred to as the Lyman series. Okay, so they are grouped under the Lyman series. Then those coming from the third to the second, from the fourth to the second, from the fifth to the second, from infinity to the second are grouped under the Palmer series, okay? While those falling from the 4th to the 3rd, from the 5th to the 3rd, from the 6th to the 3rd, 7th to the 3rd, infinity to the 3rd are grouped under the bracket series. Those falling from the 6th to the 5th, like that, are grouped under what we call the bracket series. You have the Fun series, you have the Humphrey series, and all that. So that is just how it works. Now, the first line of the bracket series, we have N1 and N2. N1 simply signifies the series, while N2 stands for the level where the electron is falling from, okay? So the first line of the Balmer series actually has N1 as 2 because it is the Balmer series. Then the first line is falling from the 3rd level to the 2nd level. So automatically your N2 is 3. So you can actually find the 2nd line of the Balmer series, 3rd line of the Patchen series. You can give those multiple exam questions for your students to play with. And then that takes us to the wavelength. These electrons fall with a given wavelength. They fall with a given velocity. So the velocity with which these electrons will crash at each of these levels is given by the reciprocal of lambda, which is the wavelength, which is equal to Rydberg's constant, open a large bracket, 1 all over the square of N1 minus 1 all over the square of N2. N1 signifies the series where all of them are falling to, while N2 signifies the level where they are coming from, okay? So you can always make your hypothesis right. Then the Rydberg's constant is 1.097 times 10 raised to power 5 per centimeter. You can always convert that to meters. And remember, examiners at times will want you to put your answers in nanometers, okay? So you can always do that. Nanometer is 10 raised to power minus 9. Remember, milli is 10 raised to power minus 3, micro 10 raised to power minus 6, nano 10 raised to power minus 9, pico 10 raised to power minus 12, femto 10 raised to power minus 15, acto 10 raised to power minus 18, zemto 10 raised to power minus 21, yocto 10 raised to power minus 24. The last 3 are the ones that always escapes your memory, and that is the acto, zemto, and yocto. Just remember AZ. AZ, Anele Dumzo Ajofo, Kano, Koro, and Obo families. AZ. So A there for acto, Z there for zemto, the Y in the Z is the yocto, right? So you can always remember that very well. So as far as the regions are concerned, the only UV region is the Lymer series. The only visible region is the Palmer series. As for the Patchen, the bracket, and the Fun series, they are the infrared region. As for the Humphrey, is the far infrared region. Then it is also important for you to know the energy in terms of electron volt at each of these energy level, right? The first energy level is minus 13.6 electron volt. The second energy level is minus 13.6 all over 2 square electron volt. The third energy level is minus 13.6 all over 3 square electron volt. So the formula actually is minus 13.6 all over n square electron volt, right? Now, this tells you the energy at each energy level, okay? Very, very important. And then it's important for you to know that this energy is equivalent to minus, that is to say, minus 13.6, sorry? All right, let me put it this way. The energy possessed by an electron at the ground state is equivalent to minus 13.6 electron volt, which is equal to minus 2.8 times 10 raised to the power minus 18 joules, okay? It's also important for you to know that 1 electron volt is 1.602 times 10 raised to the power minus 13 joules of energy, right? So at times you can be asked to calculate the difference in energy from the first and second energy level. And to do that is simply minus 13.6 open bracket 1 all over the square of n2 minus 1 all over the square of n1, stuff like that. So some hypothetical questions that can come under this series lines are, they may just one of a sudden ask you, how many spectral lines are there when an electron drops from the 5th orbital to the 1st orbital of the hydrogen atom? How many spectral lines? If you count that properly, you're going to get 4 spectral lines. Next can be, what is the wavelength of the first line of the Balmer series? So all you need is just the first line. Look for your N1 and your N2 and you'll be good to go. Now, what is the wavelength of the first and the fourth line? You should be able to hypothesize that without problem, right? All right, so we are going to be stopping this chapter here because it's getting too long, okay? This is already almost 20 minutes, if not more than, and I don't want this chapter to be very long and disturbing. So courtesy demands you have some little break. So at this point, we'll be ending the concept of quantum theory here. We'll continue in the next video. And don't miss that video, okay? Don't miss that video, because in that video, we're going to see details of the quantum theory configurations and many other things that you will definitely need for your exam. So all you need to do is to like, share, and subscribe to our channel, and then also join us in our physical and live class at Quintessence Tutorials. Okay, Quintessence Tutorial is just opposite Uniben main gate. It's not hard to find. In fact, I'm going to show you a draft on how to locate Quintessence. It's very easy. Just watch this and then you see how to locate us, and trust me, by the time you be with us, you will get more, because we can't teach you everything here online. All right, thank you. Watch this. In this video, I'm going to show you briefly how to locate Quintessence without stress. It's a very easy thing to do. First and foremost, let's assume that this is Uniben main gate, okay? Let me call it main gate, right? Now, if you follow your right, you're going to see another gate for Uniben called Uniben small gate. Are you there? And then if you continue your right, you're going to reach to Ekosodi junction, okay? These are those that live in Ekosodi. This junction connects to the express road. Then somewhere here, you're going to see the Uniben bridge, okay? That major bridge you saw. Then there's a road divider from here to here. You know, this road divider has a net in between, so you can't just cross the road when you come out of the main gate. You have to go through the bridge. Or if you're coming through the second gate, you can't just cross because of this net here. So you will have to follow your right. Now, this is a junction called 24th Street Junction. This is 24th Street Junction, okay? Now, here you will see a junction called 19th Street, 19th Street Junction. Now, straight over, you will see a street here called 24th Street, okay? This place is 24th Street, 24th Street. If you walk down the street, you're going to see us by the right. This is Quintessence. Now, this point you see here is called Christ Embassy, okay? You can see Christ Embassy from the junction here, so it's not far. It's about 1 minute walk and you get there. And then this road continues like this. So this is an express road. This is an express road. So if you're coming out from the Uniben second gate, it's the easiest way for those who live within the school campus. So once you come out of here, let's say this is you now. Yeah, so you come out from here, just walk towards your right, cross the road, come back here, and then walk down into the street, and boom, you meet us at Quintessence there. It's that simple to locate. If you're coming from Ekosodi, then you will have to cross the road as well and move towards your left now until you get to 24th Street, then enter here, okay? Next, if you're coming from 19th Street, you follow your, this is your right now. And then when you get to 24th Street Junction, you enter here. So this is the last street just before the turning point. So this is how you locate us at Quintessence. So all roads leads to Quintessence Tutorials. All right. So join us at Quintessence Tutorials, and trust me, you will be happy you did, because we have everything you need to make your A's in all your subjects. We have recorded 5.0 before, and we can do that again. See you at Quintessence. Boom.